So Steve, I will start by introducing you. It's a great pleasure to introduce Steve Laval. If you have been just close to robotics, not even in robotics, you probably have heard of the RRT algorithm, but there are many more algorithms that Steve is responsible for. Steve has written the definitive book on planning algorithms, and he was pioneering making the book freely available before it became a reality later. Steve was the head scientist of Oculus VR, which was later bought by Facebook. Steve has recently won a ERC Advanced Grant on foundations of perception engineering. I'm looking forward to hearing Steve's talk on Goldilocks and the robot brain. Steve, please.
Thank you very much. What time should I stop speaking and take questions?
You have 1 hour, including question. I would suggest stopping after 50 minutes.
Yeah, I'll do that. Hopefully sooner, but I'll do that.
Okay.
All right. Yes, just let me know. I'm watching the clock here too. So thank you very much, Danny. I really appreciate this. I was very excited to see your invitation. I met Danny over a quarter of a century ago when we were both at Stanford together. He was more or less on his way out and I was on my way in. And I didn't know anything about computational geometry then other than what I learned in motion planning, which was something significant, but I learned much more. Danny was telling me about arrangements then, and then I got to work with Leo Gibas and learned much more. And the subject is very dear to my heart. I wouldn't call myself a computational geometer because there's plenty of people who know more than me who work on it professionally, but it's always shaped my thinking as I've approached robotics. And I hope this talk brings that out. So I apologize a bit for the silly sounding talk. I was trying to maybe attract an audience. Hopefully I didn't just make some other audience run away thinking this is not too serious of a talk, but I wanted to put the perspective such that we're thinking about a robot. It's a kind of autonomous agent. It interacts with the physical world. And how big does its brain need to be to accomplish some tasks? The tasks might be clean the floors, do systematic exploration, search for a treasure, whatever the case may be. It could be a collection of tasks. And I want to figure out, through some kind of process that usually involves thinking, figure out how much is just enough, just right. So if you take away something, the robot can't possibly do it. Maybe you have a proof that there's an obstruction to solving the task. And if you go beyond and put a much bigger brain in, then you're just wasting energy and time and cost and a bunch of other stuff. So I go through the talk in 4 phases, which more or less can correspond to some levels of generality. Maybe the brains get smaller as the talk goes on, which maybe happens to all of us, perhaps. I don't know. I get fatigued, but so the first part I'll call strong geometry, and then weak geometry, with no insult intended. With the weak geometry is very close to computational geometry. You can call it combinatorial geometry if you like. A little bit of topology, and then set theory, although nothing crazy like descriptive set theory or anything, just basic sets and mappings and things. So as we look at these different levels, I want us to think about, in any areas of mathematics, the area is truly defined based on what makes 2 spaces or sets equivalent in some way, right? It's usually some equivalence relation that you start with, whether it's say it's group isomorphisms, could be homeomorphisms in topology. So we want to figure out kind of what makes sense and what parts get, let's say, sort of discarded, and that will correspond to where we move in this. And I don't think I probably need to say this to this audience, but very often to I think a more engineering oriented audience, people often think in engineering that having more knobs to turn makes something more general. And I think it's sort of mathematics, it's the other way around for the most part, right? That the more abstract and general spaces have less things that you need to define, right? That you need to have sort of working. So that leads me to the next point. The things I'll say today aren't interfered with by probability theory. So they're more or less the same ideas can apply in a probabilistic setting. They make it more complicated, but I have sort of a take it or leave it attitude about probabilities. You can put them in if you like it. You can take them out if you don't like it. It doesn't matter. But I think it's much more insightful to talk about these things without throwing a lot of probabilities around. I do think there's an obfuscation kind of factor that goes on with probabilistic modeling to a large extent. So we think about a robot and its environment's the physical world. The robot has to interact through it, through sensing and actuation. And by robot brain, I guess I mean a computer. You can put an automaton in there or cram a whole Turing machine in there if it fits, whatever you like. And so I want to just make a note of two different kinds of spaces. There's an external state space. Usually when someone says state space, depends on what field they're in. Computer science will be thinking probably of an internal computation state. A control theorist or roboticist might be thinking about more like the physics kind of state, or the phase of a dynamical system. So by X, I mean more the external, and by I mean more the internal, and I'll call those information states or information spaces. And that's where you'll find things like data structures or other kinds of things that you as computational geometers might like. So some warnings or some things to think about. I don't know if they're exactly warnings, but perspective is important. So sometimes we want to differentiate between the robot's view, like what could the robot possibly, let's say, figure out or compute with respect to its environment or do by interaction with its environment, versus the God's view. And by the God's view, I mean, as people who are trying to do analysis, what can or can't we say about the overall system? And this usually involves making some assumptions about the physical world. What space of possible environments might the robot be in? How do the sensors work? What kind of mappings do we have for them? What kind of mappings do we have for actuation? And so on. And one thing to point out, the external state space here, this physical world, does not necessarily behave like a Turing tape, unless you really wanted to. But then you have some resolution issues probably, but it doesn't matter. But I'm just saying that the interaction with the physical world is very, let's say, rich and complicated and unpredictable. And largely, it contains a lot of many-to-one mappings because you can't go and measure everything in the world. So the key to a roboticist is to try to figure out what really needs to be measured. So thus, I want to say that it's not necessary for the robot to store, let's say, a digital twin of its environment inside of its so-called head. So one way to view it is a coupled dynamical system. I won't do much with dynamical system formulations here so much, but that's one way I like to think about it. This influences me going all the way back to even my PhD thesis work. And I fell in love with this notion of information spaces, which are actually older than information theory. And they come from von Neumann and Morgenstern. So the idea of information comes from the context of dynamic game playing or sequential game theory. And it comes about in the case where you have imperfect state information. So imagine playing like blind chess, Kriegspiel it's called sometimes, or the battleship game or something. You don't know the exact state that's going on, but the players are somehow interacting. And this is, I think, very important. So you imagine it's like a game against nature, the internal versus the external, and we're trying to make something happen. But there's a beautiful symmetry to everything that's going on here, except one of them you can have a little more say over what happens, the internal one typically. Unless the internal corresponds to human brains, then it's a big mess as well, but that's not the topic for today. So I spent a lot of time thinking about how to make smaller and smaller information spaces, and maybe that's what an algorithms person ought to be doing too on any kind of context, if the internal really corresponds to the internal state corresponding to memory and code and things like that that's inside of the machine. And I've been, chapter 11 of my planning algorithms book that Danny mentioned, it was the chapter that I spent by far the most amount of time on and probably gets the least downloaded. And it's the one I'm most excited about. And I've been excited about it since I wrote it. It was really hard to write. I barely was able to put it in there, but I really feel like it's like turning everything around in the other direction, kind of from the way the book is now, which it really should. If I had another book, which one of these days maybe, it would start more with the information spaces and work its way up. Because you really have to understand, it's sort of like the foundations that would be like the, analogous to the computation model, really, of what's going on as robots interact with their world. I'll try to bring some clarity to that. But the history, this kind of history information space is the most basic one, and it corresponds to the history of all sensor observations that you might have gotten by sensing whatever's going on in the world with your sensors, and all actuation that might have been done, at least what commands were applied by the robot brain. So the memory of all of that is a history information state. The space of all of those is a history information space. The idea is to map that down to something simpler and hopefully allow it to stay in the simpler space the whole time without having to refer back to this giant history that you don't want to remember. And we see examples of this all over the place. There could be, what's called open loop control. I call time feedback, perfect time feedback. You could have state estimation. They do that. Most people in control theory prefer to just estimate the external state and be done with it. But for a robotics problem, it's pretty hard to measure everything that might be relevant to that might be that you might contemplate as being connected to the robotics problem. There's all things all the way down to the bottom. The Kalman filter ends up taking the history and transforming it into a space of Gaussians. So mean and covariance are enough to parameterize the problem. Usually it's the position, maybe position and orientation of a robot, and perhaps imagine a flying vehicle or something. So maybe the Kalman filter space could correspond to 6 degrees of freedom plus there's the means, which correspond to 6 degrees of freedom, and then there's the covariance matrix that correspond, that's roughly quadratic in size. And you might double that putting velocities in and whatever else. So anyway, that's a very general way to look at things. And that's kind of guided me for a long time. So I think it's important, we'll go back to this kind of Goldilocks sort of analogy. I want to try to find the information space that's just right. So what sort of internal representations or memory are necessary? What memory is also sufficient? And you know, we can consider a full range from just sensor feedback. Like maybe you just have a sensor that measures the light intensity level, and the motors are wired to it with no computation at all, and they just kind of rotate the robot to go to the light source. So this is a very basic kind of a Breitenberg vehicle. There's a book on these things. So that's fine. It's maybe too simple. It's hard to do much with that, but that's where you start, and then you try to add more and more. And one of the things I like to say is I imagine the environment is sort of like a massive hard drive, and you can query the environment through sensing and actuation. Well, you can query the environment through sensing, and then you can manipulate or make changes to the environment through actuation. A lot like you might interact with a Turing machine, but the kind of interaction you have with the environment as a roboticist looks pretty different. And one of the things that's a bit strange here, I think, is that you know, we want to avoid computations if we can help it. It doesn't make sense to measure a bunch of stuff, get a big data problem, and then throw a big GPU at it, and then come back and say, you know, we actually didn't need all that stuff anyway. We could have just sensed the right thing from the environment. So that's something I find very intriguing. I once, I wonder if I have time for an anecdote. So I was very good friends with Jeff Erickson and Sariel Harpaled. Their offices are right down from mine at the University of Illinois for a couple of decades. And they always had very interesting things to say. And one time Jeff would just walked into my office. He saw a PhD thesis on my desk. I was on the committee of a student of Francesco Bullo, a control theorist, very strong mathematically oriented person, differential geometer. And he opens it up randomly to a page and he goes, "That's wrong." And he just puts his finger on a theorem. And he's usually right when he does that. It's unnerving, but it basically said something like this algorithm is doing something with visibility polygons in linear time or something. And he's like, I can't be. It has to be super linear based on, you know, I can think of polygon with holes, or, well, I don't remember the details of it. But I thought, you know, this is really strange. Both these people are very mathematical. So I arranged for them to have a play date in a coffee shop for 45 minutes. And after a whole bunch of arguing back and forth, you know, Jeff Erickson's very animated, so is Francesco Bullo in different ways. But by the end of it, it became clear this kind of problem, which is for Francesco, the sensor provides the visibility polygon directly, because it's just measuring it from the world. And that looks reasonable to Francesco. And for Jeff Erickson, the computational geometer, you know, let P be a polygon, simple polygon, maybe with holes, whatever, ... So that's written down on the Turing tape. And then you do some computation, and then it looks absurd to say that you did something faster than some lower bounds. So I think you can do better than lower bounds if you let nature just do the right measurements for you. That's my ridiculous claim. So as a roboticist. So I think everyone walked away from that meeting happy. I certainly did. So let's go through the 4 levels. Strong geometry. Well, robot motion planning. I fell in love with the piano movers problem when I was a young graduate student. Worked on computer vision for 2 or 3 years, and then just dropped everything right in the middle and said, "Oh my God, I love robotics and I love motion planning." That was largely due to Jean-Claude Letombe's book becoming available, and Seth Hutchinson. I was his first student. He was a new professor at the University of Illinois, great advisor, and so I was in heaven. And then, you know, to make that kind of thing work, you have to do SLAM. So you build big maps, localize. This is getting towards this kind of maximalist approach. You're putting a lot of information into the robot. And then, hang on just a second. I feel like this feeling like I've missed something. No, I haven't. Okay, it's coming later. All right. I'm getting ahead of myself. I thought, my gosh, some slides have disappeared, but I don't think they have. So I fell in love with this idea of there's some abstract configuration space, and you go from point A to point B, and the inputs are given in some kind of strange way, because configuration space obstacles are not so easy to explicitly represent. Of course, you know, I don't want to go through the mathematical and algorithmic tools of motion planning here. I fell in love with, when I first heard about it in 1991, the Schwartz and Scherer famous cylindrical algebraic decomposition approach to resolve motion planning in a very general form. I just loved all that stuff. The semi-decidability and Tarski sentences and all of that stuff was really great. So not semi-decidability, sorry. First order theory of reals and Tarski sentences and so on. I even implemented cylindrical algebraic decomposition for a class project and got it working up to 5 dimensions, but it was only a sphere, so it wasn't too bad, but it was really cool. So I just love that stuff. There's Canny's algorithm, of course, later, and the roadmap method. And then there's sampling-based planning, PRMs, RRTs, whatever. And then there's differential constraints where, you know, you have to formulate, especially for nonlinear systems, which is what most of robotics seems to deal with. You have some maybe differential geometry coming in, and you have to deal with control systems in addition to, you know, don't hit stuff. You have to sort of move in a certain way and handle problems like momentum and the drift caused by it and so forth, and unpredictabilities and everything else eventually. So that's all fine. And that goes into like the big brain robotics, all that stuff being explicitly measured and calculated. When I think about big brains and what's kind of wrong with it, it reminds me of this idea of the Cartesian Theater by Daniel Dennett, a well-known philosopher of mind. And he was doing this to kind of poke a little fun at some other philosophers that they like to do that to each other, I guess. And also maybe some views that cognitive scientists and others may have had, where they seem to almost believe as if there's an entire reproduction of the outside world going on inside the head, and the brain uses that in order to make a decision. And there's a maybe recursive kind of fallacy that you can apply to this, and maybe that doesn't stop. Maybe that also has a Cartesian theater inside the Cartesian theater and so forth. But I don't want to go down that side too much, but I just want to say that I feel like a lot of robotics has this feeling when you want to go and measure everything, trying to create a digital twin inside of your head, that it's like this Cartesian theater going on. And I really feel like to do great foundational kinds of robotics work, something that's not computer science, not control theory, but really robotics, it's important to understand what little bits need to be in the brain. And by bits, I don't necessarily mean computer bits, but however it needs to look. All right, so weak geometry. I just want to go over some works that we did over the years now and just kind of give some examples. This one's really cute because arrangements comes up somewhere in there, and I hope Danny still likes arrangements. Maybe he's tired of them after some decades. So imagine you have a robot. It's a little disk. A point, let's say, moves around in R2, and there's a number of landmarks. They don't move. They're just some points with labels, and then you have a sensor that gives you a cyclic ordering of landmarks. And that's all it does. I think that's a reasonable kind of sensor. So you know, it's not a sensor that's giving you the roots of a high dimensional, high order collection of polynomials or something. It's just giving you, you know, this is actually very implementable, reasonable kind of sensor. It gives you the cyclic permutation. So I show one sensor reading here, which I think my pointer works, but that's cyclic. So you don't know where the start and end is. And now I give it a motion primitive. So the computation operations here, what would be analogous to that, look more like motion primitives for these kinds of problems. So I just say, go to landmark I. And while it moves, the robot can sort of notice how the cyclic permutation is changing. And probably what I say on the next slide is going to be obvious to a lot of you. But I think when you try to put it from a robotics perspective, it's kind of nice and, well, at least surprises us a little bit. But I think it's very nice. So what happens for this simple model is that with a linear number of motion primitives, you can answer any kind of questions involving convex hulls, let's say, any kind of reasonable questions. Like, for example, for a triple of landmarks, what other landmarks are inside the triangle and which ones are outside, or any other, you know, convex hull questions about which landmarks are inside or out. It's very closely connected to, of course, the dual arrangement of lines and oriented matroids and all of that fun stuff. So, what's interesting here is another story about my colleagues. We were showing some of this to, so the robot learns the dual line arrangement is another way to say what comes out of here. And I was, my student, Ben Hanin Tovar, who mainly worked on this, and we're showing this to Sabriel Harpalet, who's a very sharp guy. And he thought, well, that's not really going to work efficiently, so give up, you know, pretty close to that, you know, and we found that very discouraging. But it turns out we're not deciding whether or not some pseudo line arrangement is realizable, and we're not figuring out coordinates of some realization. Those are much harder, like the references I have at the bottom here. It actually is realizable because the robot's able to move around. I mean, it exists in the physical world, and the robot's just moving around doing some calculations building these information states. It's a kind of map, so to speak, but it's a kind of combinatorial one. So that turns out to be very efficient and easy. You're not deciding, it is realizable. So you're not given some kind of crazy pseudo lines as an input. So I thought that was interesting. So we surprised Ariel a little bit. One of my very few times I was able to surprise him. So, but that was good. You could start to get topological here. You could do this with a lot of these things. You could sort of imagine now if you have this cyclic permutation of landmarks, but then one could pass in front or behind the other, and it could start to make pretty braids. And then you can ask questions about braid groups. But I think it's like a kind of a teaser into some interesting mathematical questions, but maybe purely mathematical, because I'm not sure what the braid group relations mean for robotics for this kind of problem. But nevertheless, I was excited about braids for a while, but then never figured out how to argue that it's, well, what is the term, theoretically practical or something? I don't know. It's just, but it's interesting. So you can make a lot of nice variations by detecting whether or not the landmarks are passing in front of or behind, which is also a very reasonable operation for a sensor. We did another version where instead of the cyclic permutation ordering, you have just a combinatorial depth ordering. You can see I've been influenced by computational geometry, I hope so. So I'm not coming here hopefully just naive, like I've never heard of computational geometry before, but it really did shape our thinking a lot. So again, this is a reasonable thing. You could have these towers could be out there with radio signals with all the same strength. And on my receiver, that's hopefully with an omnidirectional antenna, I just sort them according to which signal is strongest. And then we have a primitive that says move towards and another primitive that says move away from a landmark. So you can move directly towards it or directly away from it. So by doing these things, we show that, okay, you can build Delaunay triangulations as your map of the world, and convex hulls again, if you like. Here's another one that's a little more control oriented, but it does involve this combinatorial kind of reasoning again. And it came from a lot of discussions I had with nonlinear control theorist Daniel Lieberson and my student Jingjin Yu, who kind of solved the hard problem, which was to design some Lyapunov function, and then he wrote the paper and did everything else. So, but he did really great stuff, and the implementation. But the problem is, suppose you have a Dubin's kind of two-dimensional spaceship flying around. So it's like a car that can only go forward, and it's a kinematic model. And you have not only one of them, but you have a bunch of them, and you want to get them to rendezvous. So they all just need to kind of gather together. Each one's like a point, and what they can see through their windshield is just the label of some other, let's call them robots, some other Dubin's robot. But they can't see the precise angle to that robot. And so the question is, how wide can we make the windshield? It's a windshield, but again, you don't get the precise angle. It's like a detection windshield only. How wide can you make the angle and get everybody to rendezvous? And it turns out it's close. I'm sorry I don't put the number there, but it's like almost 180 degrees. It can be pretty wide. And if there's some significant amount, like if you're not moving directly to the point, then you get this kind of spiral, the logarithmic spiral. But the spiral eventually converges anyway under pretty reasonable conditions. So we can get a bunch of vehicles to rendezvous without coordinates, which I think is nice. It's certainly unusual in the normal way that control theorists look at it. And Jingjin's Lyapunov function was not quadratic, which is like shocking to control theorists. So he had just learned the subject and came up with a very creative one. So that was really brilliant guy. He's at Rutgers University now, professor. Little touch of topology, although I'll say the topology here is certainly boring, especially if you like computational homology and persistence and things like that. I don't have that kind of fun stuff. So suppose you have a, wow, this looks like a visibility polygon. Okay, great. But again, let's think from the sensing perspective. Let's suppose you put a point robot into a polygonal environment, and then I just want to point out something that should be obvious to people in this group. There's the parts that are let's say directly visible to the sensor, and then the parts that are not. The parts that are not, I'm going to call gaps, and then I'm going to imagine that my sensor does not actually build a visibility polygon, but it just reports that there are gaps. And I want to look at topological changes in the gaps. In other words, I want to look at changes in the connected components of this boundary portion that's being detected. So that there's the kind of weak topology. It's just connected components, so nothing, no holes and twists or other weird, interesting things. So one of the things we looked at for this, one of the things we developed for this is called gap navigation trees. And this actually grew out of some earlier pursuit evasion algorithms that I developed when I was at Stanford based on our mobile robot project that Danny was right there with when we were doing this. So we were talking about mobile robots and things at the same time. And this was a collaboration with Rajiv Motwani and Leo Givas and David Lin. And I think that's it. Yeah. And Jean-Claude Latome, of course, he's my boss there. I was kind of going through the different people, and so based on that work, I tried to get more and more minimalist. That was playing hide and seek, the invisibility polygons, let's say, this was sort of what that paper was about. And then in this one, we wanted to get more minimalist and just have this basic gap detector. And so the robot goes and moves around, and as a robot moves back and forth, if you have something like this is just a generalized inflection, you can make a polygonal one if you like. You might prefer a polygonal one, doesn't matter. We assume that the robot's moving in some piecewise analytic bounded region that's connected with piecewise analytic boundary, and no sort of nasty things happening to it. And then when it crosses the inflection, then the gap will appear or disappear. And when it crosses a bitangent ray, an extended bitangent ray, then there's a splitting or merging of gaps. And so we have the motion primitive is just go to a gap, and in the process, other gaps will split, merge, appear, disappear. Only those 4 events can happen. I'll cheat like computational geometers love to do and say assume general position. A bunch of things could all happen at the same time, but let's pretend that doesn't happen. And then we can build something like this. Anyway, you see it moving around. It's just chasing these gaps, and then it builds this tree-like representation that is exactly the encoding of the computational geometers have found for calculating shortest paths and polygons. But this robot's just kind of finding it on the fly, so that when it sits in this point in the bottom here, this blue point, I'm afraid to try to enlarge it, then this is how the world looks to it. And it chases gaps, and then gaps will split, it chases more gaps, and all of the goals can be expressed in terms of these gaps. And then, so you just say, okay, I want to go to a goal that's hidden behind gap number 12, and off it goes. And what's interesting is that it can do distance optimal navigation without ever measuring distances. So it doesn't have to sense any Euclidean distances or anything. It only senses these gaps, splitting, merging, and so forth. And then it's only able to do that, but nevertheless does distance optimal navigation in a simple polygon or any sort of simply connected region with a piecewise analytic boundary. So that's the idea for that. So another thing we did was, this is just a filtering problem where you're just trying to, or sensor fusion problem, where you're just trying to keep upper and lower bounds on how many moving targets there might be in each one of the shadow components. So the shadow components here are white, and there's a bunch of colored targets that move around. And one thing you can very efficiently do, which Jingjin Yu figured out, is that as the robots, the white disks, move around carrying these visibility kind of sensors, all we keep track of is these shadow components splitting, merging, appearing, or disappearing. And based on that, it turns into a very simple integer linear programming problem to maintain tight upper and lower bounds on how many targets there might be in each one of the shadow components, based on color as well. So we put colors there so that it has a whole range of possible distinguishabilities. They could be all the same color, or each one a unique color, or anything in between, and it all sort of works nicely. So that's another kind of thing we're able to do. So here's just a demo, just showing that through these critical changes in the sort of topology, but just being these combinatorial changes in the shadow components, then we just do these simple updates. And again, it's based on this appear, disappear, splitting, and merging. We've also done some work with where you just this is just filtering for a robot, but you move the robot around, or any body moves around. It could be a robot or sort of anyone. You have these beam sensors, and then you try to reconstruct the path in some way. And we figured out conditions under which you can construct paths up to homotopy. You can also look at what sequences of regions it went through, and so forth, based on a bunch of different types of sensors. And this allows partially distinguishable sensors, beam sensors, directional ones, and so forth. So a bunch of different possibilities for that. So I want to make sure I have some time for this and the set theory part, and then I'll be open for questions. So again, it's not like intense set theory, but I'm just saying this is something that applies to robotics problems, just starting from basic mappings over sets and things, and you can replace them with almost anything. So I have the external state space, like I showed you about in the beginning of the talk, and we have let Y be a sensor output space, so sometimes called observation space. So H goes from X to Y, and this is how robots get information about the outside world. And one of the first things I want to look at is the pre-image of that mapping. So just look at a given sensor output Y. I want to look at the set of all states that could have caused that sensor reading. And think about the amount of uncertainty that's being handled here. The state space could be enormous with all kinds of attributes, all kinds of things going on. Maybe the sensor just measures the distance to the wall in the direction that the robot's facing, or maybe it just detects that the wall's been touched, and that's about all. So that's the core source of uncertainty in robotics. It's not stochastic noise and other weird things like that, or some quantization effects. Those are fine, they're difficult, but the real trouble is that the robot's not measuring everything. Maybe it's trouble, maybe it's benefit, but you don't want to necessarily measure everything, as I said. Let capital pi be the partition that's induced by any function you want to make, but certainly by these sensor mappings. And now, make some simple examples. This would be a simple detection sensor. Maybe there's 4 robots here moving around. I guess I said N in general, and then they're moving around in the plane, and I just have a simple detection region. And I guess in this particular case, this one can count how many points are inside the detection region. So that's a perfectly reasonable thing to do. Maybe it has to do, maybe there's robots moving around and this thing has a camera above, or maybe it's based on weight, but you get the idea. You can do something like this. This one feels very combinatorial. So there's these nice pre-images. There's going to be 5 equivalence classes in this partition induced by H, right? So it's very natural. There's this, remember, keep thinking about the many-to-one sort of mappings that come out of these sensors. This one's really neat. If you just take a directional depth sensor and put a robot that can translate or rotate around on the plane and put it in, say, a polygonal environment, then these pre-images become, in general position, become 2-dimensional sheets. And so you end up with a kind of foliation or nice partition of the configuration space, which is again you have the XY coordinates in the polygon, and then you have this S1 circular component that corresponds to orientation. And what you get is very closely related to some of the structures that were developed for motion planning for a line segment robot a long time ago. But what I haven't seen, and maybe some of you can correct me if I'm wrong, but I haven't seen anyone try to compute this kind of structure for, let's say, for anything really, for any polygons or disks or whatever you like to do. But I really think that there's an interesting structure here. This partition that you get just based on a simple depth sensor, it just points in some direction, gives a reading, and I want to know the set of all places where the robot could be, all configurations where the robot could be based on that, given that the polygon, let's say, right? So I think I think that structure will tell us some interesting things, and I don't think I've seen that before anywhere. Correct me if I'm wrong, but I think this is an interesting sort of collection of open problems here to look at. Now, if we then want to compare the power of sensors. So I want to say, when is one sensor better than another? Well, it's hard to do that with physical sensors, but with these mathematical models of sensors, we can say that one sensor dominates another if and only if the partition is a refinement. And this makes nice sense. And what it implies is that there exists this function G, so that if H1 dominates H2, then that means we can transform the output of sensor 1 to simulate the output of sensor 2. So that's what this just based on refinement of partitions, it means there exists a function. Now, does there exist a computable function? Well, I don't know. I mean, it depends on the problem, right? But just want to point out this structure very generally, though, because if you don't have this relationship, then there does not exist such a function that can do this. So it's very important to see this before even bringing computation into the picture, let alone efficient computation. So you can start arranging then all of the sensors into a sensor lattice. You can start thinking about, for a given state space X, this is the external state space, what are all possible sensors? And you can define an equivalence relation and say they're the same sensor if they have the same partition, if they induce the same partition of the state space. And now I can arrange everything into a sensor lattice. And at the top, we have any bijective sensor. It is so powerful, it can measure everything. And at the bottom of the lattice, you have a dummy sensor. And you can consider things like greatest lower bounds, least upper bounds, and so forth. So this is just a picture of a partition lattice. So you end up with a partition lattice, but the state space is usually bigger than 4 elements. It could be quite complicated, but I still think this notion is very useful that, as I'll describe a little bit more in a bit, you're traveling around through these sensor lattices as you do sensing, filtering, sensor fusion, and even robot navigation and planning. So let me give some examples of these concepts in terms of spatial and temporal filters. And generally, you could talk about spatiotemporal filters that mix them. So there's this ancient idea of triangulation. I'm sorry, it's not the triangulation that you guys tend to love. It's not the one that Chazelle solved in linear time, but this is the ancient notion of triangulation used for measuring like how tall is that mountain over there based on a couple of angles. And so this notion of triangulation is very broad and really just corresponds to intersecting preimages. When you look at all these methodologies, they're just intersecting preimages. For example, stereo vision, the preimages are rays. And so if I have calibrated camera system, I intersect two rays. So it's an intersection of preimages to figure out where the point is. I have this ancient principle of triangulation is based on the angle between two landmarks. So holding the angle fixed, the preimages give you a circular arc, or actually two circular arcs if you're not sure which side you're on. It depends on whether or not you know the ordering of the landmarks. And if you want to do a full, what do you call it, like localize yourself, figure out the precise point, then you do triangulation. You apply this principle to intersect two circular arcs to find out where you're at precisely. So that's the ancient principle of triangulation. Trilateration, same thing, just distance from a tower. You have the dimensionality goes down with each tower in terms of the preimages. Eventually, you have 2 points in 2 dimensions. You have 2 points for 2 towers, and then you have a unique point when you put the third tower in. Hyperbolic positioning looks at the distance. What do you call it? Relative distance between landmarks. It's actually relevant for things like submarine localization. It was used in World War II. So you get hyperboloids in that case. Now let's introduce time. So we introduce a time interval, call it t, and then I'll have this state time space z. I'm not going to do weird curvy relativity stuff. I just think of state time space as just extruding the state space with just one more dimension, much like you do when you do motion planning for a bunch of moving disks where you know the trajectories of the disks, let's say. And now, okay, and now, oh, okay, fine. Then I can talk about state trajectories, which are just mappings from the time interval into the state space, right? So it either makes a pretty picture in Z, which is a drawing, or you can then it kind of shows the explicit time parameterization, or you can draw it like this, like we often do, and then you wonder what's the parameterization of the curve underneath, but it's parameterized by time. So this one I'd have to show a movie to make it clear. So we can make sensors over space-time now, over state, sorry, that should be state-time space. So we can make sensors over that and just have the mapping go from Z to Y now. And then we can make partitions, preimages, partitions, and a sensor lattice over Z space now. So now it's actually considering time. And we can go another step further. Oh, I guess here it is. So now in addition to that, we can do triangulations over this. So now you can consider doing intersections of these preimages over Z space, and that captures what's going on, for example, in a global positioning system, where time measurement is very critical to the localization, in addition to other intersections that are occurring. Now, in practice, there may be some noise that's occurring as well, and some redundancy is built into all of these methods. You may want more sources of information than just the bare minimum here, but I'm moving along at the minimum, showing how these methods are designed really and what the insights are. And again, I think it's all just insights of pre-image intersections. Now we extend over to these state trajectories, which I've already introduced, and we can make history-based sensors. They map from the history. In other words, a state trajectory gets mapped into an observation. An example would be an odometer, like in a car or on a robot. It's telling how far the robot's traveled. You read it, it says 3 meters, but it's taken a while to do that. So it's a trajectory goes in and a reading comes out. Well, why not make partitions over this function space then and make a history-based sensor lattice? And then the notion of triangulation becomes like a ski slalom. You have different times at which you've got observations, and now the trajectories have to go between the ski gates. And so that's the kind of picture that things will generally look like in this kind of broad setting. So why not? So all these filtering methods, again, it could be like non-deterministic versions of Kalman filters and other things like that. It could look like a kind of slalom, and you're just trying to fit all the things, this is the nominal sort of, let's say, design of the method, is trying to explain that trajectory based on the observations. So the trajectory has to go through all the gates. So just a summary of these partition lattices. You can make them over the state space, state time space, even the trajectory space. And then I view sensor fusion problems as traveling around in this lattice. And triangulation is moving up in the lattice. Triangulations are trying to move up in the lattice, but you might go down in the lattice because of additional uncertainties like unpredictability in your motions, or the interaction that you do with the environment may cause you to go back down again. And your goal is not necessarily, and usually not, to get to the top of the lattice where you know everything. The goal is something else, to make sure you're high enough in the lattice to solve your problem. And that's all you need. That's the only place you need to be. So we have, going further down this path of minimalism and using some of these concepts, we started making the motion primitives more complicated, just using a billiard bounce. There's a lot of mathematicians that have been interested in a particular kind of Hamiltonian system that involves doing a perfect reflective bounce off of surfaces, and then asking the question of whether or not that trajectory that you get out, if it goes on forever, is it ergodic? And at the very least, ergodicity implies that every open set will be hit. And if that's the case, then that's a pretty nice way to be guaranteed to explore your space. So we use that as a kind of robotic primitive, both in theory and in practice, and had very good luck with it. So it will bounce around at everything. There's even a paper that says for almost all polygons and almost all initial conditions, the billiard trajectory is ergodic. And that almost involves meager set theory. So it's not exactly measure zero like easy stuff. It's a little bit weirder, but anyway, it's quite impressive. So you can make a pretty dumb robot that's guaranteed to find any treasure you like if you sort of give it enough time. But it's quite impressive how fast it explores. So there's so much to be done in that case. This is a robot system where we had a 3-bit brain for the robot. And there's 2 of them, actually. There's 2 mobile robots here. They would be going around clockwise, patrolling. And I have a condition that I don't want the 2 robots to be in the same room. I want to have at least one of these tape boundaries separating them at all times. That's all they know about, well, they don't know much, but all they do is implement this policy, which triggers whether or not they bounce off of the tape virtually. They go up to the tape and turn around and come back, or do they pass through the tape? So that's the only decisions they get to make. Otherwise, they just do these billiard bounces inside of these regions. So do billiard bounces, but whether or not you consider this to be a wall, the white, the yellow, or the red, is based on this tiny automaton, right? Sorry, 4-state automaton, 2 bits, I guess, yeah. So it's a 2-bit brain robot. So that shows like very little feedback information feedback, very tiny information space doing something reasonably useful. So some final thoughts. Again, don't try to sense everything and then perform intense computation to get what you need. And sense only what's needed. It's the power of forgetting. It's like forgetful functors in category theory or something. It's important to forget and not ever measure or worry about stuff. Don't handle a bunch of uncertainty that you didn't have to measure. I think this is very close to Brooks's subsumption architecture comments, where he said the world is its own best model. But I follow a lot of his philosophy, and I think it was interesting at the time. But I think what's different here is that I would sort of say, I've already said it, maybe the world is like a giant hard drive that you interact with. The interaction is sensing and actuation, but don't measure more than you have to. And that's what sort of fits to me. So I think regarding machine learning, which is certainly on the rise in robotics, the Goldilocks principle still applies. And I want to know, what are the right sort of minimal structures? If you have some space you're optimizing over, are you sure these minimal structures are even in the space? Are they represented? Are you going to find them? So I still think it's very important, even to guide learning. And finally, we want to match these structures to the tasks that we're interested in. I think I keep bumping up against computational geometry in this quest to understand robotics, partly because I like it, but also because in the same way computational geometers are minimizing complexity, time, space, whatever resources you want. And that's all fine, but it's usually in some sense already in the robot's brain, like they've been given a problem, let P be a polygon. And I'm sort of saying, well, let the environment be this that the gods have imagined, and they have a space of possible environments. And then you have to build these mathematical models of like these sensor mappings that I've talked about, and also actuation models that go and interact with it. I'll leave you with one little puzzle. I'm sorry, it's not like Danny's wafer problem puzzle that he had everyone intrigued with a couple of years ago in Mexico. This one doesn't involve solving a problem. So I'm sorry, I'm just going to explain it to you. But I think it's amusing because it brings a lot of concepts together in something very, very simple. So I have a robot, reminds me of a SLAM loop closure problem. And the robot is in one of 2 environments. We don't tell it which one. It's either environment A, which is in the XY plane, on a circle, or it's an environment B, which is on a helix, and I don't, yeah, so it's on a helix, and that helix projects down onto the XY plane. And its commands are just, add theta, subtract theta, whatever. You can just change, where you want to go and say your polar coordinates with a fixed radius. So task one is, I tell you, there's a treasure, go find it. You can go around one full cycle, and let's say you can sense the XY position. You go around one full cycle, and then you can say, well, I must be on the helix. You can conclude that, right? And then if you want to find it on the helix, what do? You start behaving like a coiled up lost cow, right? So these online algorithms things, you can go up a turn, down a couple of turns, go back and forth, solve the recursion, and I don't know what you do. You double how far you go each time or something like that. I forgot what you do to get the best competitive ratio bound or something, but you can do that. But I find task two more amusing. Determine whether there is a treasure. This is what leads to like this kind of semi-decidability and sampling-based motion planning. Robotics is filled with these kind of problems. Oh, now you have to decide whether or not there's a treasure. You go around one full cycle and you think about what the robot knows here. Well, what does the robot know after one full revolution? The robot can say either I'm on the circle and there's no treasure, or I'm on the helix and there may or may not be a treasure, which I think is very interesting because the kind of, let's say, pre-images or information states, when analyzed in this case, it's like a very simple example, but you got this kind of decidability affected by simple loop closure, simple topology, covering space sort of example here. So I just feel like a lot of things are coming together in like the simplest kind of example I could think of here. So that's where I'll stop. Thank you.
Thank you very much, Steve. I suggested people will open their mics and just start asking questions. You don't have to ask for permission. If anybody wants to ask a question, perhaps, Damon, let me read. It's a very enjoyable talk. Thank you. I'm sorry that I have to leave you to another meeting. But now questions. Steve, let me be the devil's advocate. The one that doesn't care about climate change and big data centers, and ask you, okay, I have a lot of sensors and I have a lot of computation power and storage. What do I gain from this minimalism?
Well, one thing you gain, which is what I hope we try to do in universities, is understanding. I want to understand what needs to go into the robot's brain to solve tasks. And with the ERC, we're actually looking both at humans and biological organisms together with robotic systems and wondering, why are the formulations different on either side of the fence? One of the reasons why is because we did not design ourselves. But I think these kind of insights that you get, like I talked to Manuel Bloom a long time ago because I always loved his paper on exploring mazes with pebbles and the compass, I think, or I forgot the exact title of the paper right now, but it's from the 70s. And he was saying he thought about that. He had the idea of that paper because he was thinking about ants following each other around on the rim of a kettle, until they just fall off and die because all they know is to follow the next one, kind of. And so it's very natural to think about these kind of questions. And I think they're very insightful because, again, you're coupling the task you want to achieve, the problems you want to solve, so to speak, together with what information is necessary. And I think it also leads to a kind of obstruction theory, leading, telling you what you certainly cannot do, what would be ludicrous to try to do. And I think these are very insightful things. And I'll just go back to saying this is, maybe it's kind of hidden from, if the problem for you starts with it's been described on the Turing tape, let's say, and now you have to design an algorithm, then you have not been handed the opportunity to do a serious reduction in complexity, right? Because you could have just left the irrelevant information out there in the world and just cleverly query what you need. That's kind of what I learned by doing this gap navigation trees. I learned some things from computational geometers about what's really critical in visibility problems. And then I'm like, hey, we can sense exactly those things. And we can even say that that's the part that you have to be most robust about. Like, this is the critical part that you need. These are the critical events. This is the critical stuff you need. So you ought to be designing your sensor to obtain that, not just put a bunch of stock commodity sensors, cameras, depth sensors, lasers, all the junk everywhere, and then go deal with it later. Then I'll hand it to you guys and you just deal with the mess, let's say. And then we say, oh, please, NVIDIA, build me a GPU to solve this.
I completely agree with you. Questions? Anybody? don't hesitate.
May
Stefan?
I ask a question? Hi.
Sure.
Thank you for the talk. I would like to know, are you also interested in reinforcement learning? Because I would like to believe that your research would be very valuable here. I mean, there's this huge problem of how to reduce the state space and so on to improve learning progress over epochs and so on.
Yeah, that's a great question. And in my thesis work in the early 90s, early to mid 90s, about 2/3 of my thesis was value iteration. And, it was value iteration applied to even like stochastic non-holonomic planning problems. And so there wasn't any, I guess the reinforcement learning stuff was maybe happening while I was working on these things. I figured out these kind of methods by reading old papers by Larson and Casti in the 1960s, which were then, just kind of derived from Bellman's optimality work,
Yes.
more like optimal control kind of work.
Right.
Not so much the dynamic programming work that you see in computer science, but a different path that looks more like dynamic.
Temporal difference learning, yeah.
Yeah, exactly. And so, I did some work with interpolation over continuous spaces and obstacles and all that stuff. So I've been in love with that topic for quite a long time. We didn't call it learning then. Now it looks like reinforcement learning has kind of rolled the learning problem into the optimal control problem, is how it looks from my perspective. And that's all sort of good and fine. But then I sort of ask, well, I don't want to make the machine learn more than it has to. And I don't work on the problems directly. So I would like to talk to learning people and say, yeah, maybe, these kind of structures can help guide what you ought to be learning. Or if you're doing, say, some kind of policy iteration, maybe the space of policies are things you haven't even considered before, because you're not maybe aware of what types of minimal structures might exist. And so I think there are a lot of good possibilities. But if it's going to be sort of, turn the crank, do Q learning, I don't know, and some extension of value iteration that just adds the learning problem into it, which is quite clever and pretty, but it just makes the problem sort of harder, but not necessarily leading to more insight. That's how it looks. Maybe there's a lot of recent work that I don't know about, but that's how it looks to me.
So may I add a question here? Because so when we talk about reinforcement learning, the new hot stuff is deep reinforcement learning, where you have a deep neural net or so, which at the end, the output layer tells you what to do, which, the evaluations of your possible actions. Yeah. And so what people need to do is to reduce the complexity of this net. So what we would have done before this deep learning stuff would popped up was feature selection and feature engineering, right? But here, and this is where my question comes, the less interesting thing is I have an input space X, which I see like an R to the N, and select some dimensions, but create new ones, like using singular value decomposition or a non-linear combination of features to construct new features. So in terms of your talk, this would probably mean maybe not only what is a minimum set of sensors or so, but also how can I combine two sensors to form one, which kind of has the most valuable information from a certain angle of view.
Mm-hmm. Oh, still there?
Right?
Yeah,
right. Mm-hmm.
Yeah. That's hard to say. I think that I think deep learning is powerful as a tool to show that certain things can be solved in certain ways, and I think that it doesn't provide a lot of insights into the things that I'm interested in directly, I guess, from what I've seen so far. In that a big network with a fast GPU that can do whatever billions of inner products as quickly as you like. It's fascinating that such a simple kind of method running on a huge amount of data with this one kind of structure that's being optimized can do the things that it can do. The world has never seen that combination of that amount of data and that amount of computation coming together. And I have a sneaking suspicion that some other simple algorithms are out there as well, that if someone built a fast enough processor for them and threw the right things at them, they would also yield interesting things as well. And I think that in some sense the game is on for that, but that may take some number of decades. That I'm not sure what's going to happen in the future for that. But in any case, I do hope that maybe this understanding, I try to contribute understanding, I hope, and I hope that this understanding maybe might give people insights into what can be done. It doesn't end up looking like a deep network at some point, but maybe there's some other space of structures that you're optimizing over, and that might be quite fine, because a lot of these methods end up boiling down to stochastic gradient descent, which, by the way, was the basis of things like my Oculus Rift head tracking, which was closely related to sampling-based motion planning. So all these, somewhere under the hood, there's a lot of similarities between these kinds of methods and things.
Okay, more questions? So let me thank Steve again for the very educating and eye-opening talk.